Section 6.1, exponential growth and decay. We've got the exponential function there on your screen. It's called an exponential function because, lo and behold, the variable, the x, is an exponent. That's why it's called an exponential function. So in chapters 3 and 4, we talked about polynomials where x was the base of an exponent. In chapter 5, we talked about x as underneath a radical. Today, in chapter 6, moving forward, we're going to be talking about when x is an exponent this time. So, a couple of quick notes with exponential functions. Your a value here, this number out front, it cannot be 0. And that should make sense because if this was 0, this is 0 times anything, and 0 times anything is always going to be 0. So just know that your a value cannot be 0. You're not going to run into any situations where that happens, but just so you are aware. And then your b value, there is one other thing here with b. b is a positive number. It's always going to be a positive number. Let's try that again. Positive other than 1. It can't be 1. It can't be a value of 1 because if this was 1 to any power is always going to be 1, so it's never going to change. It's going to be the same y value every time. What I want to do now is just highlight some of the differences between growth and decay. I'll try to leave this function up here as much as I can. So with growth and decay, actually, one thing that is the same with growth and decay, a is always going to be bigger than 0. We're never going to have a negative number. The a value will never be negative in our exponential function. Okay. The only time it would be negative, we could do some transformations where if it was negative, it would be a reflection in the x-axis. But we're never going to really be focusing on that. When we talk about real life models, which we're going to do a lot of with exponential functions, your a value is never going to be negative. You're never going to have a negative number of people or a negative deposit. You're never going to deposit negative $200 into your bank account. Okay, so your a value is going to be positive whether it's growth or decay. The difference between growth and decay is that your b value, let me go back to the pen, your b value in growth is going to be bigger than 1. Okay, and this is called your growth factor. Okay, growth factor, that's b. Okay, in decay, the b value is not going to be bigger than 1. It's actually going to be between 0 and 1. Okay, not equaling 0 and not equaling 1 either, because we said b is a positive number other than 1. And if it's decay, then it's not going to be 0 either. Okay, the difference, and by the way, the b value when it's decay is the decay factor. Okay, decay factor is your b value. Whether if it's a decay function, if it's a growth function, then your b value is your growth factor. Okay, the general picture, the general shape of these functions, if it's a growth function, so you got your x and y axis, growth functions look like this. Okay, it's not a straight line. It's not really a parabola either. Okay, notice that this is eventually going to just keep going parallel to the x-axis. It's never going to get all the way down to the x-axis. I'm going to define that here in just a second. But as you go to the left, this is never going to get to the x-axis. For a decay function, it looks very similar, except it just kind of looks like a reflection in the y-axis. Okay, we just kind of flip it over the y-axis. So now this time, as we go to the right, the line is going to get closer and closer and closer to the x-axis, but we're never actually going to get there. And that term, or that idea where we're going to approach something, but we're never going to touch it, we're never going to cross it, is called an asymptote. Okay, it's a vocabulary term, asymptote. A graph approaches, but will never touch or cross. Okay, in this case, in these functions, and I'm going to put a little star here, it's usually the x-axis. Okay, in our exponential growth and decay functions, our asymptote is usually the x-axis. Now, if we have a vertical translation, then our asymptote might change a little bit. But if we're not doing any vertical translations, then the asymptote is usually the y-axis. So as we go to the left on the growth function, we're going to get really, really close to the x-axis, but we will never cross it. As we go really, really far to the right on the decay function, we'll get really, really close to the x-axis, but again, we will never touch it or cross it. So that's kind of a basic overview of exponential growth and decay functions. Let's actually do a couple where we have to graph. So directions say graph the function, tell whether each function represents exponential growth or decay. Now, we don't have an a value in this one, so when we're talking about what number represents what, our a value in this one is going to be 1, and then the number with the base on your exponent is always your b value. So this is not 2 times 1 to the x. This is 1 times 2 to the x. So our b value here is going to be 2, and we'll deal with that here in just a little bit. Now, when you graph, and this is very important that you get this written down, or just make sure we have this as an understanding. When you graph these exponential functions, I want you to make an XY table, and I want 5 spaces. The 5 x values I want you to use are going to be -2, -1, 0, 1, and 2. Those are the 5 x values that I want you to get used to using, because that's really going to give us the best picture and make it the easiest to see. So how do we find the y values? Just like we do with every other function, to find the y value, we're going to take these x's and we're going to plug and chug them. We're going to put them right into our x. So I'm going to do this in blue. We're going to start with 0. So we'll say y is equal to 2 to the 0 power, and anything to the 0 power is going to be 1. Okay, whether it's 2, whether it's 5, whether it's 100, whether it's a third, whatever. As anything to the 0 power is always 1. Okay, let's move on to the right. 2 to the first power is going to be just 2. Anything to the first power is itself. Y equals 2 squared. 2 squared, I think you can handle, that's 4. Okay, so as we go to the right, 1 times 2 gives me 2. 2 times 2 gives me 4. So if I go to the right, it's like I'm multiplying by 2, so then it makes sense. Then if we're going to the left, we're actually going to be dividing by 2. And if we want the math behind it, we can say 2 to the negative first power. Let's try that again. Negative first power. We can make that positive by taking it down to the bottom, 1 over 2 to the first, and 2 to the first is just 2. So we can say that 2 to the negative first is equal to 1/2. And then if we want to do the same thing with negative second, that's perfectly fine. 2 to the negative second power becomes 1 over 2 squared, and 2 squared is 4. So this is going to be 1 over 4. So as I move to the left, and that's a really bad 4 here, let me just switch that there. So as I move to the left, I keep dividing by 2. So if I keep dividing something by 2, I'm never going to actually run out of something mathematically. Now, if I keep cutting a piece of paper in half, and then in half, and then in half, and then in half, it's going to get to the point where I don't have anything that I can cut. But mathematically, I've never run out of anything. I've never gotten down to 0. And that's kind of the big idea of the asymptote. And I'll show you what that looks like here in just a second. So if we're going to graph this, and we can graph this, so we have our x and y axis, 1, 2, 1, 2, 1, 2, 3, 4. We can put our points on the graph. We have 0, 1. We have 1, 2 right there. We have 2, 4 up there. And let's see, -1/2 is about right in there, and -1/4 is getting closer to the x-axis, might be right in there. So when we draw our curve, and it's important that we draw our curve here, we're getting steeper as we go out to the right, and as we go to the left, we're getting flatter and flatter to the x-axis. What I see a lot of times when people first start doing this is they just kind of take this down and then they cross it over the x-axis. The x-axis is never going to get reached. So it's important that you flatten out that line and make it parallel to the x-axis as you go farther to the left. Now, we said the b value here is 2. If we go back to our table, b is greater than 1, which means it's a growth function, and it has this general shape. Our graph just had that picture. So this one is a growth function. Okay, let's try another one here. Y equals 1/3 to the x power. Again, we're going to make an XY table. We're going to make 5 spaces, -2, -1, 0, 1, and 2. Okay? 1/3 to the 0, just like we had earlier. Y equals 1/3 to the 0 power. Anything to the 0 power is 1. 1/3 to the first power is going to be itself 1/3. 1/3 squared. So if we have y equals 1/3 squared, that's 1/3 times 1/3. 1/3 times 1/3, it's going to give us 1/9. So 1/9 there. So as I go to the right, I'm either multiplying by 1/3 or the same thing is dividing by 3. So if I'm going to go back to the left, I'm going to end up multiplying by 3. So 1 times 3 is going to give me +3, and 3 times 3 to go to -2 is going to give me +9. Okay, so when we go ahead and graph here, let me draw in my x and y axis. 1, 2, 1, 2, 1, 2, 3, 4. Draw in what you can. So we got 0, 1. We have 1, 1/3. Might be right in there. So 2, 1/9 is going to be really, really close to the x-axis. -1, +3 is on the graph. Now, -2, +9. I didn't go all the way up to 9, and that's fine. Only graph what you can. If your graph only gives you this much space, then only graph what you can. Okay, so this thing's going to be pretty steep coming out of there, and then we're going to get really flat going along the x-axis as we go to the right. Now this one, I hope you can see that your b value is 1/3, and if your b value is 1/3, that's between 0 and 1, that's going to be a decay function. It has this general shape. It's getting smaller as we go to the right, so this is a decay function. Exponential equations have a lot of real-life application. Okay, the two biggest that I can think of are money and population. Okay, if we're talking just population or number of objects, this is the model we're going to use right here on your screen. Y equals A times the quantity 1 plus or minus R to the T power. And I'm going to talk about all of these here just a second. So the A value, this number right here, represents your initial amount. Okay, it's what you're starting with, whether that's a number of people or a dollar value, things like that. Initial amount. Your R value, we'll do that one in purple. The R value is the percent increase or decrease. Whoops, decrease. Okay, and the key here with the percent increase or decrease, it has to be in decimal form. So if it's a 5% increase, your R value is going to be 0.05. You need to turn a percent into a decimal. Okay, so if you ever see the percent sign, that is a percent. You need to turn that to a decimal before you can put it into your formula. Your T value, T always stands for time, whether it's math, science, doesn't matter. T represents time. Usually it's in years. Okay, might be in months, might be in days, might be in weeks, we don't know. Usually it will be in years though. And then your Y value here, this number out here, is going to be your final amount. Okay, whoops, final, N-A-L, final amount. It's what you end with. Okay, or it's what you're at a specific time value. Now, this plus or minus, if your function or if your situation is a growth function, if we want growth, we're going to use plus. If we're going to have a decay function, if we're losing value, we're losing people, then it's going to be minus. But the other variables mean exactly the same thing. Initial amount, growth or decay rate, time, final amount. The only thing that's going to change is this plus or minus. Okay? So, let's try an example here. The value of a car, Y, in thousands of dollars can be approximated by, and I'm going to give you this formula. It's going to be Y equals 25 times 0.85 to the T power, okay, where T represents the number of years since the car was new. Question number 1 then says, is the model growth or decay? Well, if this was a growth function, 1 plus something, we're starting at 1 and we're getting bigger. There's no way that 1 plus something is going to be less than 1. So it's got to be 1 minus something. So that means it's got to be a decay function. So we'll write that in red. This is a decay function. Whoops, we'll just leave it at decay. Is the model growth or decay? It is decay. Okay, question number 2 then says identify the percent increase or decrease. Okay, so with this value, the percent increase and decrease comes from here. We need to solve for R. We know it's a decay function, so we know it's 1 minus R. Okay, so we can say that 1 minus R is equal to, and that's what this is, 0.85, 0.85. And we need to solve for R. When we do that, we would have to subtract the 1 and then divide by -1 to switch the sign on that. After you do all your work to get that, you're going to find that your R value is 0.15. Now, this is the percent increase or decrease as a decimal. We need to turn this to a percent. To turn a decimal to a percent, we're going to take this decimal point and we're going to move it 2 places to the right. So this is going to be 15%. So what that tells me is that every year that I own this car, or every year since the car has been new, that the value of this car has gone down by 15%. Okay? Question number 3 then says estimate when the car will be worth $8,000. This is where you're going to use technology and your graphing calculators to make your life a whole lot easier. Rather than just kind of guess and check and figure out, and it might take you 15, 20 minutes to figure out a Y value that makes sense, we're going to use our calculators, our graphing calculators. So, in the Y equals screen, and this is the Y equals screen over here, just hit the Y equals button up top, type in your function, 25 times 0.85, and you have to use X because that's the variable. We use T normally, but T represents X here, okay? After you type this in the Y equals screen, go ahead and hit second graph, and then you're going to get a table. Okay, look at the table. The question's asking estimate when the car will be worth $8,000. Now remember that Y is in thousands. So at time 0, you can see this here, the car's not worth $25. That means the car's worth $25,000. So what we need to do is we need to find a Y value of 8. And it looks like we get one right there at year 7. Okay, so estimate when the car will be worth $8,000. That's approximately, and we can say approximately year 7 or after 7 years. Okay, we're going to use our technology here to our advantage to save ourselves a lot of time and a lot of headache trying to find the right number. So we know from year 7 we're at $8.01 thousand, and then in year 8 we're under $7,000. So sometime in year 7 we went from we crossed that $8,000 mark, or our car was worth $8,000. Okay, this is a pretty accurate statement of what happens with cars. As soon as you drive it off the lot, it's losing a ton of value. So 7 years after you paid $25,000 for a car, you're going to get less than 10 for it. So that's just kind of a little gross realization, or kind of a depressing realization, that new cars, and cars especially, do not hold value at all. Okay, so just kind of a little real life heads up there. Let's try another one here. In 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Question number 1, write an exponential model giving the population after the year 2000. So now we're not given the function, we need to write it, okay? So what we're gonna do, we're gonna start with, and I'm gonna flip back and forth here a little bit. We need to figure out our initial amount, okay? So our initial amount, what we're starting with is 6.09 billion. I'm not going to put the bunch of zeros in there. I'm just going to have 6.09. So I'm going to start this. Let's see, my y value was in green when I underlined it. So let me switch to green here real quick. So we're going to have y equals my initial amount, and I'm just going to go back and forth. Let's see, my initial amount was in blue. So let's see, my blue is going to be 6.09. And then I'm going to have times 1. And if we're growing, it says increased. We're never going to decrease, or never going to have increase and have minus. So it's going to be plus. We're increasing by about 1.18%. Let me just make sure I got my colors right. So I'm going to have in purple. I need to turn this into a decimal. So this is going to be 0. To turn a percent into a decimal, we're going to take the decimal and go 2 places to the left. So it's going to be 0.0118. Okay, so 0.11. Whoops, that's not even right. 0.0118. And we'll close it off with a purple just because that's lazy. And then I believe the time was underlined in red, so we're going to have t. So this is going to be our exponential model. What we're starting with, what we're growing by, we don't know how many years yet. So giving the population after the year 2000. Now when we get to question number 2, when we estimate the population in 2000, that is a y value of 5, or a t value of 5, not a y value, a t value or an x value, depending on the variable, of 5, because it's 5 years after 2000. So let me switch to green. We'll just say y equals 6.09 times 1, and you can combine these two if you want, 1.0118. 2005 is 5 years after, so we're going to make our t value 5, and this is something you can type in your calculator. Okay, type it in exactly like this, 6.09, parenthesis, 1.0118, parenthesis, raise it to the 5th power. The calculator will do the order of operations for you. Okay, when you do this, you're going to get something along the lines, and I'm just going to round to 2 decimal places. It's going to be 6.46, and this is in billions. Okay, 6.46 billion people in 2005. Question number 3, estimate when the population was 7 billion. This is something we're going to use the calculator for again. So in the y equals screen, I've changed it now to our function, 6.09 times 1.0118 to the x power. And now I need to figure out when the population was 7 billion. So now I'm looking for a y value of 7. You're going to need to scroll in your table, and it looks like I crossed the 7 billion point, or I'm right around 7 billion in year 12. And 12 this time actually means, let's see, sorry, where was it? After 2000, sorry about that. Had a little freeze up there. So we're talking years after 2000. So this is 12 years after 2000. We crossed that 7 million or 7 billion point. So we're going to say approximately 2012, because our t value is 12, and we're talking years after 2000. Okay, so 12 years after we crossed that 7 billion mark, so we're approximately 2012 for when our population was 7 billion. Now, there's one other formula. I said something about money. If you ever deposit something in a bank, or if you ever take a loan from a bank, this is the formula they're going to use to figure out interest. Okay, A equals P times the quantity 1 plus R over N to the NT power. Your A value here We're just going to do all these in one color. Your A value is your final balance or your current balance. Final balance. Your P value is your principal. Principal, just like you would spell like Mr. Thomas, principal. The principal, in case you don't know, is your initial deposit. It's what you're taking out. It's what you're loaning the bank. Initial deposit. It's called the principal. So if you take out a loan, then your principal is how much your loan is for. If you deposit something in the bank, that's your principal. It's what you're giving the bank. Your R value, just like in the last example, your R value is your interest rate. Interest rate. And again, that needs to be a decimal. So if it's 5%, that's going to be 0.05 as a decimal. Your N value, this is the one that confuses people a little bit. N value is the number of compounds in 1 year. So this might be something to jot off to the side. If it says compounded quarterly, there are 4 quarters in a year. So your N value would be 4. If it's compounded monthly, there are 12 months in a year, so you're going to have an N value of 12. If it's compounded daily, 365 times, because there's 365 days in a year. If it's weekly, it's 52. Annually would be 1. So it's not how long or how much time has passed in between each compound, it's how many compounds in a year. And then T, just like in the last one, is time, and this one is definitely in years. Okay? Notice your N value appears twice, one in the bottom of a fraction, one is part of the exponent. Just keep that in mind. Got a couple of examples for you. You deposit $9,000 in an account that earns 1.46% annual interest. Question number 1, find the balance after 3 years if the interest is compounded quarterly. This is something you can type in your calculator. Okay, the equation, the formula would be something like this. It'd be Y or A equals, your principal is $9,000, 9,000 times 1 plus your R value, your interest rate is 1.46%. So that's going to be 0.0146 over, now we're compounded quarterly, that means 4 times, so our N value is 4 to the 4 times, and we're talking 3 years. That's your formula. And I've got that typed in right here in my calculator screen. When you type this in, you can type this in exactly how you see it just in the calculator. The only thing I would tell you, if you have an older one, where when you hit the exponent button and it gives you something like this, you need to put 4 times 3 in parentheses. If you want to just make it 12, feel free. It's going to give you the same result. But if you have an older calculator, make sure you put 4 times 3 in parentheses. If you actually have a calculator that will put 4 times 3 up in the parentheses, or up in the exponent like mine does, then you don't need to put it in parentheses. But if you have an older style one, you do need to put it in parentheses. Okay? When you put that in your calculator, all you need to do, type this in and then hit enter. And we're talking money, so we're going to round to 2 decimal places. We are looking for a balance, or we're going to have a balance of $9,402.21. This is your answer. If you compounded quarterly after 3 years, you would have $9,400. If you're compounded daily, that changes just a little bit. That changes your equation just a touch. The only difference is the N value changes. Daily means 365, so our N value is going to be 365. I'm going to have 365 in both places, just like I have 4 here. The 4s now are going to become 365. When you type this one into your calculator, again, we're talking money, so you need to round to 2 decimal places. Even if that second decimal place is a 0, it still needs to be a 0, because we're talking money. Money is always rounded to 2 decimal places, regardless of what number that second decimal place is. If it's a 0, write the 0. If it's compounded daily, your account balance, keeping everything else the same, 3 years at 1.46% interest. The balance after 3 years is going to be $9,402.95. So after 3 years, you're going to make about 74 cents more if it's compounded daily. Obviously, this changes the longer you wait and the higher the interest rate, the more different these two are going to be. Okay, if you can ever find an account that compounds daily with a really high interest rate as a savings account, definitely take advantage of that. Loan rates, the lower and the less often, definitely the better, because this would be what you paid back. If you take out $9,000 and pay it back in 3 years, you're going to pay the bank $9,400. Save yourself 70 cents if you can get it compounded quarterly.